Alright, hello everyone. I just wanted to make this video real quick since it's been a while since I've taught anything, and I kind of wanted to teach you guys a little something about how an AI actually, works. Since this is a topic a lot of people don't really know anything about, especially the finer details on it, and that can lead to a lot of fear about what is this thing. So I'm actually going to walk you through this deep neural network I made a while back, and go through it all with you. This is all written in Python, and you can see this is the whole file. I'm going to walk through this. I'm going to discuss with you guys what exactly AI is and what it's doing here, and we'll just go ahead and get started here. So we should start by talking about the architecture of a neural network. Neural networks are basically multiple little layers or steps along the way to creating an answer. So maybe we get some sort of a input, and then maybe we do something with that input, and then we send that to the next thing, and maybe that does another thing, and then eventually that leads to some sort of an output. That's the primary basis between a neural network. Now each of these little steps along the ways are what are called layers. So typically in a neural network we have an input layer, an output layer, and then any amount of hidden layers. Usually we describe it as having n hidden layers, n standing for number or just any integer. So the goal of a neural network is to take that input and slowly change it to give you an output. Now what we're looking at here is specifically a neural network which it's a supervised model. Supervised means we give it the information, and we give it the training information, and then we give it the actual answers to it so that it can learn from it. So let's start by just talking about this a little bit here. So here we've got an x value and a y value. These are just going to be the basics for our prediction. So our goal is to essentially get this x value to make this y value. So this would be our input data, which would be 24, and this would be our output data, which is a 1. Now, obviously, with actual neural networks, we're handling thousands or tens of thousands, millions, billions, tons of different information. But here, for the sake of simplicity, I just wrote, x value and y value. This is an older program of mine where I was just testing out creating one of these from scratch. So this is what we're working with. We're working with 24, and we want to get it to 1. So now let's actually talk about how we're going to do that. To do that, we're going to use weights and biases. So a weight is, if you remember back to math class, you've got this formula, which is the formula for a straight line, where y is the y point, m is the slope, x is the x point, and b would be your y-intercept. We can think of these weights and biases very similarly to that. Instead, we have basically our y would equal the weight times the input plus a bias. That's essentially all it is. It's almost, one-to-one with this line formula. So when you think of weights and biases, just think of the line formula. Weights get multiplied by the input, and the biases get added at the end. So let's talk about how we determine these weights and biases. We start by, because this is a supervised model and we don't want to actually write all the rules for it, in fact we don't even know the rules, we're essentially just going to randomize things. We set all of these weights to just be random numbers. This specific function here, random, see, it returns an x value along the interval 0 to 1. So some number that can be 0 all the way up to but not including 1. So that's how the weights work here. At least that's how this random function works, although we will be manipulating these weights and these biases later. Here you can see the biases are 0, just so that we can start out with a baseline. Next up, we have a learning rate. This is a pretty simple concept. All a learning rate does is try to slow down the amount of change over time. That way you aren't having super big changes all the time, and it's slowly learning. Now let's talk about some of these functions here. A function is in Python uses this keywords define or def. Here we've got a function for the sigmoid. Sigmoid is a special mathematical function. Basically, it returns a number depending on, the x value, the weights and the biases. So in this case, just the x value that goes into it. It will return a number between 0 and 1, and that is not inclusive. So 0, 1. That's the interval it returns it on. So depending on what number you plug into here, you'll get something between 0 and 1. These are really good for really basic probability distributions, namely binary cross entropy, which you can see here. We're essentially doing a binary cross entropy. Binary cross entropy just means that the number or that the prediction is one of two things, hence binary, meaning 2. So in this case, it's just y value of 1, so our output should be really close to this 1 by the end of it. The sigmoid function, you can always look this up. It's just, a function used for graphing things. It's defined as 1 divided by 1 plus e to the negative xth power. In this case, we do x times the weight plus the bias because we manipulate it. We also have a hyperbolic tangent function, which is similar to the sigmoid, except a hyperbolic tangent returns a number along the range of -1 and 1. So whatever gets plugged in will be somewhere along this range, not including those endpoints. And now let's talk about these inverses. These inverses are simply the derivatives of the functions. You can always look these up like I did, rather than actually calculating them. Sigmoid is very easy to understand. The derivative of a sigmoid is just sigmoid times 1 minus sigmoid. It's super simple to understand. The hyperbolic tangent is this whole mess. I'm not going to go over it here. I just looked it up and read some papers on it and found that this was essentially how you calculate it. So we'll get into why these derivatives here are important later when we start talking about backpropagation, but that's for later. Lastly, we talk about just this cost. All this cost function is just saying how far off we are, and we'll get to this also when we start talking about backpropagation. But that's enough looking at these functions. Let's actually dive into the code here, the real code. So in order to actually train a model, we need to go through it multiple times here. Sorry, I'm looking back at this code here, just trying to figure out what all of it is because it's been a while since I wrote all this. But we can see we start out here by doing forward propagation. So there are two main steps in using a neural network. There's forward propagation and there's backward propagation. Forward propagation is going through each layer and applying the activation functions, which can be these sigmoids, these hyperbolic tangents, ReLU, a whole bunch of other ones that I don't have here, and then eventually getting to a result. Backwards propagation is going back through that and adjusting the weights and biases so that the prediction gets closer to accurate. And that's the whole idea of a neural network. Essentially, we just tweak it using math. So here we go through and we need to figure out how we need to basically go through all the layers. So in the past, we've already determined these weights and these biases. The biases were just set to 0 and the weights were just random numbers. That's all they were. So now we're actually going to go through here and do the forward propagation. The way I have this neural network set up is it has an input layer, then it goes to a hidden layer using a hyperbolic tangent, then a hidden layer using a sigmoid, and then the output layer is also a sigmoid. As we know, the predictions here they use, it's a number 1. So we can consider this binary cross entropy, hence why I used a basic sigmoid function. So we go through, we get our first value. So our first layer, we have an x2 value equal to the hyperbolic tangent of those input values times the weights plus the biases. And all of that gets run through a hyperbolic tangent, which is this. You can probably look up this formula if you'd like. Hyperbolic tangent is basically, it's similar to a typical circle or typical tangent, except it relates to an arc, a hyperbolic arc. And really, you don't need to know too much about that. It's just a useful formula for activations in neural networks. Then, now that we have these x2 values, we send it on to the next layer, which is here, it's a sigmoid function. So we pass those new values we just evaluated from the hyperbolic tangent, multiply it by the weights of this layer, and add the biases of this layer, then sigmoid that, and now we got our x3 values. And our x1 value was just our input. In this case, it was 24. Then we make our prediction. Our prediction is just going to be equal to another sigmoid activation function, and it's going to take in those x3 values from the previous layer, multiply it by those weights, then add the biases, and then doing that whole sigmoid. And then we have our prediction. Now this prediction is going to be wildly far off, so it's going to need some tweaking. This is where we start figuring out backpropagation, because all of what we just did here right now was forward propagation, and we actually got a prediction by the end of it, although most likely this prediction is not going to be anywhere near our actual value of 1. So we need to go back through it and do backwards propagation. Backwards propagation can be done in a lot of different ways, like most things in neural networks, but typically it's done using what's called an error gradient. Now, typically when we think about, our inaccuracy or something, we just look at how far off we were. But there's a problem with this in neural networks, at least in big neural networks. How far off we were depends on, it is spread across these 3 different layers. So we don't know, we can't just say, okay, we were 4 off, so subtract 4 from this. We can't just do that. We need to go back through each of these layers and adjust them a little bit. So we need to use an error gradient rather than just subtracting the loss or something and then tweaking things that way. So it starts by just calculating the cost or the loss of the entire thing. So we take the prediction and the y value. Here I call a function I named cost, but it's really a simple function. It's just the actual value of that input minus the predicted value. So, like I said, it's just how far off we were. This is where the calculus part comes in. In calculus, we have concepts called derivatives. A derivative is essentially the slope at a point, or an infinitesimally small change over time. So it could be thought of, it is a slope, a microscopically small slope. So it's basically the slope at a point is what they kind of define it as. So derivatives can be, in the case of this, we usually use the derivatives of our activation functions. So here I calculate those 3 things. I'll get into why we do this here in just a second when we start going through the entirety of backpropagation. So now let's talk about this. This is a for loop. It says for I in range 250. This means it will repeat all of the code here, 250 times. So let's actually talk about this. This is the I believe I just called this the derivative weight 3. So with forward propagation, we go from the first layer to the second, to the third, then to the nth layer, however many times you have to go, and then to the output. But in backwards propagations, we go from the output and then backwards through it. So to the n minus 1, and so on. So we go backwards through it. But at each layer, we need to slightly adjust those weights and biases so that it gets closer to the actual value. This is where our error gradients come in. These are calculating the error gradients. To calculate the error gradients, we take in the input, or at least for weights. Here I didn't put anything with biases in here, but the bias formula is pretty simple. The only difference is it doesn't account for, I believe it doesn't account for the values going in. I'll discuss that in a second here. So these are each of our error, this is our error gradient overall right here, which is essentially the loss at each layer. So here, for this third layer, which is, this would be our output layer right here, which was a sigmoid, we take the derivative of the sigmoid 2, which we calculated right here. Derivative of sigmoid 2, which was the values going in with the weights and the biases. So it's just like what we did up here, same information as before, but it's just the inverse. That's what we're getting down here. So we take the values going in times the loss, which we calculated up here as the actual value minus the predicted value, and then we multiply that by the derivative of that activation function given those parameters. Now, let's actually discuss what all this means here. The loss is just how far off we were, and this only occurs in the final layer. You could see it doesn't happen on these two. The values going in is just important to know what was going in to calculate how far off we were. And then the derivative is used as sort of a pointer to how important this layer was, or like how much this impacted the actual final result. Because if this layer is doing a huge change in numbers, then we want it to barely change it. So that's what this does. That's what the derivative does. It tells us how important this layer is, essentially. That way we don't make a super big change to it. And that's the whole idea behind error gradients. These next two are very similar. We take the whatever went into it. In this case, we times it by the previous layer, which was dw3, times, obviously, the inverse of the activation function. And you can see we do the same thing here for this first layer, except we use the derivative of the hyperbolic tangent function because that was what this first layer was. Now we need to do what's called reweighing. Reweighing is just adjusting the weights. And this is pretty much the final step in backpropagation before we start back over to the next epoch. So calculating the new weights is as simple as adding to the weights the derived weight times your learning rate if you want to. You don't have to times your learning rate. You don't have to have a learning rate at all. I choose to have one because it helps to slow down the change. And then we do it all over again. We do the forward propagation, then we do the backwards propagation, the forwards propagation, the backwards propagation, and slowly it's going to move closer and closer to the actual value. So let's actually look at this in practice. Here I have it print out the prediction each time. So we'll just go ahead and run it here. And we can look back at the way start here. We can see its initial prediction was 0.61, which as we know our actual value was 1. So if it's learning, it should get closer and closer to the value of 1. And we can see as it goes on, it keeps increasing, and it gets up to about 0.77 before it runs out of epochs. But if we were to simply increase the number of epochs, we can see it gets even closer. And if we run it again, we might get different results. If we really wanted to get a super accurate model, we might do more. Although we got to be careful with how many epochs we do here. Epochs just stands for iterations, just how many times we go over it. And that's how it learns. But you can see it increases over time. So clearly it's working. This is the fundamentals behind like all modern neural networks and all modern AIs. It's just a bunch of math going through here and slowly manipulating those values over a long period of time. And you could see it's a lot of work, it's a lot of iterations, a lot of times going over the data over and over and over again. Because if I change this to like 5, you can see that's super inaccurate. In fact, it doesn't really know what it is. It's just a ton of practice, essentially. That's kind of the fundamentals behind how an AI works. I wanted to show this off just because, one, it's fun to go through all this code with you guys, and two, I figured you guys might want to know how it actually works. It's not magic or anything. It's just, well, some math, and some pretty simple math once you really dive into it and look at all of it. This is a super, super simple model, and I don't even know if I labeled this right as a deep neural network, because it's not really a deep neural network. It's looking at one x value and outputting one y value. But this does work with bigger models with a lot more data. And you always want to expose your AI to lots of data just so that it actually learns to interpret the data rather than memorize it, which is also why we usually keep these epochs lower. That way it's trying to draw conclusions from the data rather than just memorizing it. That's about it. I kind of just wanted to walk you guys through all this. Lately I've been working a lot more with natural language processing, which is similar to this, very similar to this, except it revolves around words and making predictions with words and how to respond to things. But this is what goes on behind that. All right, I hope you guys enjoyed this.